I'd like to welcome Jared McLean back to the podium. Jared is a alum of the program, and he's now a senior research scientist in Google's Quantum Artificial Intelligence Lab. He received his PhD in chemical physics from Harvard University, where he specialized in quantum chemistry and quantum computation. After that, he was the Louis W. Alvarez Fellow in Computational Science at Lawrence Berkeley National Laboratory, and from there he went to Google, where he now works on developing practical quantum algorithms for quantum simulation and other problems. His broad research interests include those subjects plus numerical methods and optimization. Let's welcome him.
Great. All right. Thanks a lot for the introduction and for the invitation to be here. Just want to say it's a great privilege, and I'm very honored to come back and be able to speak at this fellowship review that's done so much for me personally and professionally. And so I'm really happy to be able to share some of the stuff that we've been working on recently, and also to kind of bring to a broader scope some of the recent developments in quantum computing that I'm sure many of you have heard so much about. So maybe I'll come out from behind this podium just because I like walking around a little bit. But so I wanted to first mention a little bit about my career path, as many of you might be thinking about what you're doing next. And I thought you might appreciate knowing how I got to where I am today. So of course, something that played a huge role was my work in graduate school and the CSGF program here. And I'm actually very thankful to the CSGF program for taking a chance on an interesting topic a while ago, which, even though quantum computing's in the news all the time today, when I was starting my PhD I guess it was about 10 years ago, I received some reviews from other agencies that said things to the effect of, quantum computing is a field doomed only to make hard problems harder, and if you want to be a real scientist, you should consider working in a real field. I was like, oh, that's a harsh thing to say in an anonymous review to a first-year PhD student, but okay. So thanks for taking a chance on a kind of speculative area that was a crossover between new computing and HPC. So I really appreciate that opportunity to be an early mover in this resurgence of quantum computing. And while I was here, it really helped me gain some perspective on different problems in computing. I learned more at these conferences than I think I did at many others. And it built a great community and really connected me to the labs. As David mentioned, I ended up having a great time at Lawrence Berkeley National Lab, working for some amazing researchers there and getting to collaborate on topics I didn't think I would be able to otherwise. And then you might be wondering about this move that I made to the Google group. It says, why would someone working in quantum chemistry and quantum computing be of interest to Google? And I think I'll try to tell that story a little bit as I go along. But yeah, I really just wanted to say that there are many opportunities for the skills that you're learning here and the people that you're networking and connecting with right now. So you should really appreciate these conferences and appreciate this program for the foundation I think it helped build. So getting into quantum computing, so you've probably heard a lot about this recently. If you've been paying attention to any news articles, you basically can't avoid it. And so you might be asking yourself, well, is now the time that I should be paying attention to quantum computing? And so I wanted to paint what I believe to be a little bit of the timeline of how things have gone recently. So quantum has had a few ups and downs over the years. I've graphed as kind of a cartoon, on no official metric, the excitement about quantum computing as a function of time. And right around 1994, a guy named Peter Shor came out with an algorithm for factoring products of large primes, which posed a threat to a lot of the modern types of encryption that we use on the internet today, in particular the initial asymmetric key exchange. And so that scared a lot of three-letter agencies, and the interest peaked a little bit. But then people kind of realized, well, these systems are really hard to build. It's on the border of, can we even ever build them? And so excitement dipped a little bit. But then very recently, I would say a combination of things in both our understanding of how to correct errors and also our hardware has gotten a lot better. And so very recently, we've had qubits that have beat what's called this error correction threshold. And what that means is that if I could take that unit and replicate it at sufficient quality, then I can overcome these issues people have worried about, that these computers, their information gets destroyed very quickly, and I can start to do arbitrary length computation. So if I could just tile and repeat what I have now, there's a roadmap towards doing very interesting computations. And for many companies and for many agencies, this meant it was no longer an impossible question of physics. It was just a really, really hard engineering problem. So that became a risk worth taking. And I think that's going to continue upwards until perhaps this year or into the near future, where people are shooting for this achievement called quantum supremacy. So that's a very grand and somewhat ominous name. So let me tell you a little bit about what that is. And it's a task that is a well-defined computational task that we hope to do on a quantum computer and race it against the best classical supercomputers or collection of cloud computers that we have available to us, and show a massive separation in time scale. So something that might take, say, seconds on the quantum computer might take 100 million years, or the equivalent on a supercomputer. The catch will be, and you'll see a lot of press and news about this, and people will get pumped and say a lot of crazy things. The slight dip that's going to come after that is they're shortly going to realize that that supremacy task, which everyone is focused on, is not one that immediately leads to practical applications. There's still some amount of gap between that and using the quantum computer to do really interesting and value-adding propositions. And the big win after that, of course, if we get to error-corrected computation, which requires sometimes a very large overhead, then we can do all these provable algorithms like Shor's algorithms and others I'll talk about. But there becomes a big question of what we're going to do in this intermediate term, sometimes called the NISQ era, or noisy intermediate scale quantum. And that's a lot of the area that I do research in, about how to get to early applications, whatever those applications might be, including simulation of science problems that we think might have some of the lowest abstraction overheads to getting to useful and interesting computations. So what are the early application areas that people actually expect to make a big impact here? Some of them are, for example, optimization problems. So in particular, combinatorial or discrete optimization. People are looking at how computers might impact these problems. And another big one is quantum simulation, which is one that I'm going to talk about. And what that really means is just using one controllable physical system to model as closely as possible a different one, which I don't have as much control of, but have a lot of interest in. For example, I can make a very precise digital representation of, say, the quarks and gluons in a nucleus, or the atoms or electrons and nuclei in a protein, and try to simulate them as precisely as possible. And so when we talk about why we're going to use a quantum computer, it's a bit different than sometimes the discussions you hear about building, say, FPGAs or GPUs or highly parallel systems, and that we're not trying to enact some very fast or very high constant factor speedup. We're trying to change the scaling of how we approach the problems fundamentally. So we've identified some classes of problems, for example, where we get what's called a quadratic speedup. And to give you a feel for what that might mean on certain instances, so of course this is up to numbers that you choose, you might be able to take a problem that previously took a year and turn it into 2 weeks. And then actually for quantum simulation problems, we're targeting an exponential speedup. And in practice, we found problems where this might mean that problems that previously took 10 to the 82 years might be doable in 300 seconds. So that's a pretty unfathomable number. So I looked up on Wikipedia for you the age of the universe in years, which is about 14 times 10 to the 9. So you can kind of see that really the way of reading this is it takes something that was just impossible before and makes it relatively routine. So this is, of course, the grand goal. We haven't achieved this yet. And such a speedup might require quantum error correction, which is some years in the future. But this is the kind of thing that we're shooting for important problems like simulation of molecules and chemicals. So I know that this audience is relatively broad in the sense that many of you are applied mathematicians who might not have seen quantum very recently. You might be chemists, biologists, generally have an HPC background. But I just wanted to emphasize what I mean by quantum when I say quantum. So I don't mean Duracell quantum or quantum energy healing, for example, if you've been to any of the woo-woo places recently. What I mean is kind of this distinction between basic classical physics. So if I have this beanbag game in my backyard where I'm tossing it through these holes, if the beanbag goes through one or the other, it kind of is what I expect. Whereas if I cool things down or have a system that is small enough and well controlled enough, in the quantum case, if I were to actually throw that beanbag through two different holes, that beanbag might be able to interfere with itself. So that kind of strange physics allows you to use certain operations that are not available to traditional computers. And so what I'm going to say as a quantum system is a physical system operated in a regime where we need effects like discrete energy levels and interference to accurately describe it. So to some extent, everything is quantum, but if you go hot enough or you go large enough, you start to lose the ability to see and use these effects. So we're going to talk about systems that are operated in this quantum regime, basically. So which systems are these? They might be ones that are perhaps the superconducting qubits that we have or others. But actually, a lot of them, the early simulations, kind of mirror what we did classically. So this is an orrery that actually, what it is an analog simulation of the planets. And it was kind of the predecessor to digital computers. And we apparently were using these as early as 125 BC, or that's what some people tell me that this crusty relic is. And so it was actually an insight that if you were able to make these simulators of classical physics, why not for quantum? And it was actually Richard Feynman that had the insight that, well, you know, if we have this huge overhead, if quantum physics is so different than classical, maybe we should use quantum systems to simulate other quantum systems. And this was kind of the origin of the earliest parts of quantum simulation that eventually led us into the era of quantum computation that we have today. And so what are these quantum systems? So I've just thrown up a few examples here. You've probably seen a lot of pictures of these dilution refrigerators in the news, which are not actually the quantum system, but just what we use to put these superconducting qubits, which are featured here, into the state that I mentioned, something cold enough that we can actually control and manipulate it. So on the order of millikelvin, or a thousandth of a degree above absolute zero, is what we use these fridges to bring these systems into for. But we also have systems like trapped ions that people might use, or photonic systems. And really, it's this characteristic that it's any controllable system that you need quantum mechanics to describe. So often, these two-level systems can be quite general, and there's trade-offs between a lot of them. And we personally at Google are focused on the superconducting qubit architecture at the moment. So quantum simulation was this idea proposed initially by Richard Feynman, which this kind of picture here is meant to depict that you can, as if these quantum particles were on marionette strings, control them in a very precise way and make them dance exactly like the system that you were interested in. So these systems follow a very predictable pathway, which is you prepare some quantum state that you're interested in. It represents a molecular system. You evolve it for some amount of time, meaning you act as if it had the interactions of the system you're interested in. And then you importantly measure only the information that you're interested in. And that's going to be a recurring theme for some of the speedups that we want to get out. And I'll use this notation occasionally that I'll introduce, which is some state in a vector space and some energy. But kind of getting back to the conceptual part, quantum simulation looks a far cry from things like quantum computation. So making a particle dance looks a little bit different than factoring products of large primes, solving linear differential equations, or solving linear equations. And so for that, we really lean on this abstraction into qubits that you might have heard of, this quantum generalization of the bit. So it can be 0, 1, or anything in between. And importantly, it's an abstraction that lets us get away from the underlying physical system. So I no longer care that it's superconducting qubits. Now I can do everything in this abstract language of zeros and ones and start to formulate things that might look like actual computations. So just to give you a little bit of background in this abstraction, so if the classical bit is 0 and 1, the qubit is, as people say, 0, 1, or anything in between. And really, it's a state in this vector space that's sort of spanned by this 0 and this 1 state. So it's been said that if you understand the algebra of 2x2 matrices, you understand all of quantum computing. It's more or less true, but perhaps there's a few steps between that and profit. So there's these quantum circuit diagrams that are often used. I won't make heavy use of them, but to just introduce it, You read them like music notation from left to right, so qubit 0, 1, and 2. I'll do some action on each one of these, and each one of these actions has some matrix representation, which is simple. And actually the way, and I'll give some particular concrete examples of this later, but the way we translate this into actual hardware operations is each one of these can sort of be calibrated and memorized as an operation, so say a pulse sequence in superconducting qubits. And then we simply look them up and apply them as we start to manipulate the state. And as we chain many of these together, it will form some algorithm that we have. So even though it's a circuit, we use this kind of as a quantum source code, you could say, even though it's done at the level of logic gates. So I think it's important in any talk like this, as we introduce parts of quantum computation, to debunk a few of the myths that get said more commonly in the literature or in the popular news about quantum. And so one, I think, is that it's faster or better because it can use an exponential number of states. So if you think a little bit about what classical computers do, they also use an exponential number of states in the number of classical bits. You can just count 0 and 1 and 2 to that power. So it must be that it's something a little bit different than that. And the closely related one is that if it can be, well, it must be because it's between 0 and 1. And if that were true, then it would be sufficient to have what's called an analog classical computer that can actually dial between 0 and 1. So it's not true, actually, that that is sufficient to explain the power of quantum computation. You actually need at least a little bit more than that, which is that qubits can go not only between 0 and 1, but they can entangle with their friends and therefore occupy a volume of space, which is then doubly exponential in that particular size. And I think the actual most important one was exemplified by this SMBC comic authored by Scott Aronson, which is, it says, the important thing for you to understand is that quantum computing isn't just a matter of trying all of the answers in parallel. So this is the one that gets repeated most often, which is that if you have a quantum computer and an algorithm which acts on a single input, it is true that you can superpose any number of inputs you want, essentially, and run on all of them at once. But except in very special circumstances where those answers and those computations interfere in the right way, sampling the output is not really any better than randomly selecting one of the inputs. So in most cases, that parallelism doesn't buy you anything. It's only in a few cases we've found where it's exceptionally helpful that it's absolutely key. But it's important to remember. And so a lot of these are kind of half-truths, and they can be hard to distinguish. But you have to remember, I guess, the devil is in the details. And if it were true that we could simply do massive parallel on everything that we care about, then we would pretty much be done with quantum computing already. So what are the challenges in quantum computation? What are the things that we face day to day to make these really work? So if I boil down to each of these three steps that I mentioned, prepare some state, evolve it to make it look like something else, which might be your computation in some cases, measure what I want. So each of these has challenges. So for example, the number of qubits. So in your processor today, you probably have a 64-bit processor, but you probably haven't found yourself limited to problems that fit into 64 bits. You might have found that it works, in fact, on larger data sets, surprisingly. That's not exactly true for problems currently on quantum computers. In order to leverage this huge speedup that we get for certain algorithms, we do actually seem to need to fit the entire problem in the quantum computer. And so we're working on ways to make sure that that's not true, but it's a little bit of a limitation for us. Another is called coherence time and fidelity. And so I'll use these words probably a couple different times, but coherence time really means the amount of time my noisy quantum computer can keep information stable inside it. And these times can be very short for some systems, on the order of, say, microseconds, 30 or 50 microseconds. And fidelity is the kind of how well I can do an individual operation. And so without quantum error correction, you're very limited in the amount of operations you can do before the information in your system sort of falls apart. So you have a time scale problem, which is if your algorithm doesn't fit in the time scale of your device, do you get out any interesting answer at all? And then, of course, you have this measurement problem, which I'll exemplify in a slide or two with a particular example, which is you're going to be asking for specific pieces of information in this problem, and you're not going to have perhaps the same readout. Because if you had an exponential amount of information and you read out all of it, clearly you can't get any speed up. So I tend to sit in this camp of wanting to co-design better algorithms. And while perfect hardware will solve everything, I'm not sure that we'll ever have perfect hardware. And so I think it's important to meet at the intersection, sometimes in a co-design point of view, to try to have algorithms that target what hardware can do today and to push the hardware to do what we want in near-term algorithms rather than just having this long-term vision. So sometimes for quantum algorithms, you have to think a little bit differently in order to get the speed up. And this has been one of the challenges of making just general purpose quantum algorithms. So it is not true, for example, that you can just take any algorithm off the shelf, run it on a quantum computer, and expect to get a speed up. And so this has been the major challenge in coming up with new and interesting applications. So if I take a problem that's fairly familiar to the people in this room, just the classical AX equals B, where A is some matrix, B is some vector, and I would like to write down the entries of X, the solution to this translates to writing down the entries of X. So if I tell you that there is a quantum algorithm that can obtain an exponential speedup on this problem, you'd say, oh, cool. And then you'd think for a couple seconds, and you say, wait a minute, that sounds impossible, because this only took a time that scaled maybe linearly in the size of the system if it was a kind of sparse problem. But even writing down the entries would have taken me linear time. So if I can't write down the problem, how can I solve it in faster than that? And the solution to this quandary is actually to change the problem statement a little bit. So if my solution translates to preparing the state X from which one can sample, which is different than writing down all of the entries, now I can attain an exponential speedup over the classical case, and I can do something useful, which is, it's kind of a way of reformulating it so that I'm solving the problem but not reproducing the classical algorithm. So for example, if I have a scattering problem on a massive mesh of points, say looking at radar cross-sections, but I only want to know one number, and I don't really care about the details of every entry point in the mesh, then I can produce this solution and sample from it in a time that is much, much faster than what I could do classically. But in order to get that speed up, I really had to not just say, take my best equation solver, conjugate gradient, or some reduction of the matrix and translate it into quantum. I had to really think about, OK, what's the problem I want to solve, and what new tools in quantum do I have to do that? So it's a little bit of a different setting than you would have traditionally. And actually, this issue of kind of switching the problem over happens in the background in classical algorithms sometimes. It's a personal interest of mine. This is done a little bit in Monte Carlo algorithms, but you can ask me about that later if you're interested. So getting back to the application areas, so I'm going to try to dive a little bit more into the science that I actually work on. So just to remind you, the areas that people are interested in, these early areas, you'll notice that, for example, cryptography doesn't make the list. That's not because we're not interested in it at least a little bit. It's because the resource estimates for cryptography are such that if we had those available, we would have already been doing pretty interesting problems in quantum simulation. So we're focused on the interesting science problems before that, also because they're an interest of mine. So I'll be focusing in on simulation of chemistry, but others like to think about simulation of nuclear physics, or the relation representations in quantum artificial intelligence, or optimization problems. So when I talk about simulating chemistry, this will be old hat to some of you in the room, so you'll know exactly what I mean. But for those of you that don't, I'm going to talk specifically about what's called sometimes the electronic structure problem, which is if I have some idea of the structure of my atoms and molecules in my system, and I would like to gain some amount of understanding of that system. So perhaps how it absorbs light, how it complexes with other species, or how those atoms or molecules like to sit on a particular surface. And just from that structure, I would like to gain this understanding and then bootstrap that understanding into some kind of control. If I know which functional groups on a system control the absorption, I might be able to engineer new or better photovoltaics. If I know how species complex, I might be able to control the misfolding of proteins to prevent disease. And if I really know how things interact with molecular surfaces, then I might be able to design new catalysts to put in my catalytic converters. And you might say, well, this dream sounds very grand, but in a very naive sense, it's already solved. So what I mean is that there's a famous quote by Paul Dirac that says, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws lead to equations much too complicated to be soluble. And actually, written in their most innocuous form, it essentially amounts to digitizing or putting on some discrete grid where the electrons over here can sit and writing it as this linear eigenvalue problem. So it looks very innocent written in this particular way. And so you might say, well, why is a linear eigenvalue problem not completely solved? And it turns out that the difficulty in this problem is related in a very fundamental way to the strength of quantum computers. So how big might the speedup be for some of these systems? So just as I mentioned before, this is just kind of a recap of what I said. We're going to target particular systems, but we're hoping in this case for an exponential speedup. And this is sort of related to what I mentioned, which is the challenge of chemistry is the same as this power of quantum computation in a more general setting. And so if I coarse grain what I mean by this problem statement, so basically what we're asking in this molecular modeling case is where the electrons like to sit around an atom and molecule. This is going to let us predict all of those properties that I said we were interested in. But at a basic level, we know in this room that you always, when you're solving some differential equation, have to chop up space and choose some discretization to solve it in practice. In chemistry, we have very specific discretizations that are often quite good based on our knowledge of the problem. These basis sets that we choose are very handy. And if you imagine that there is m of them in my system and I have a single electron, this problem has dimension m. And then if I have two of them, there's, roughly speaking, before antisymmetry, m squared places to put them. And you can kind of see where this logic is following, which is to say that if I have 100 places to put it, so just 100 boxes for my simulation cell, and 80 of these particles, the dimension of that fairly innocuous eigenvalue problem is now something like 10 to the 160. So that's a fairly daunting number. To help you get a feel for it, I looked again up on Wikipedia. The number of particles in the universe is about 10 to the 80. So this means it's as if there was a kind of universe within every particle in our universe, and I need to enumerate all of those in order to solve this problem exactly, which is a cripplingly large dimension. But it's actually, if you think about it, this is the natural space in which quantum particles explore. So if I have a controllable quantum system that I can make look like this chemical system, then I don't have to write all of those numbers down. I just make one system mimic the other and only extract exactly the information that I'm looking for. And this is kind of the essence of what we're going to do. We're going to do it in a digital way with a bit more tricks, but that is essentially what we're trying to do. And to help you get a feel for this, you might have seen kind of these exponential distributions before, but in the context of probability distributions. And so if you have, say, some set of places you like to go for lunch, this is a very short and caricatured view of it, you might have some personal preferences. Person 1 and person 2 has their own personal preferences. And sometimes we model these types of preferences in some compact representation like a neural network. But if person 1 has no interest in person 2, then the probabilities would factorize, you would say, and the storage is, say, then just linear in the number of people. However, if you have some community of people with interesting relationships, either friends or enemies, this might not factor. And so storing that joint distribution can start to scale exponentially. And so you say, well, that's true of things that interact in probability distributions also. What's different about the quantum case? And it turns out there's a very subtle difference, which is our distributions might be complex valued. And this allows sort of people to interfere in this kind of now very stretched analogy in a way that makes it hard to predict exactly where they're going to be or what they're going to do. And so there's actually a very close analogy between classical neural networks or deep neural networks and quantum circuits which have parameters in them that we can adjust. And so this is actually a connection that people have been exploring somewhat fruitfully in the context of quantum machine learning, I would say. So I think it's important to emphasize that we're not just interested in quantum computing in the abstract. We're trying to get towards interesting real problems that people want to know the answer to. And so to zoom in on one in chemistry that's been highlighted a fair number of times, we're interested in this problem of nitrogen fixation. So what do I mean by that? It's this chemical process, which has been grossly simplified by this equation, by which nitrogen in our atmosphere makes it somehow into our plants and into our food. So this, in some extent, is fertilizer. And humans largely do this process via the Haber-Bosch process. And actually, current estimates say that this consumes 1% to 2% of all energy on Earth. This is largely done in factories in Germany at the moment. And it's currently run at 400 degrees Celsius and 200 times atmospheric pressure. But you might be thinking, well, plants were around before humans were, so how is that getting done? And the answer is that nature has figured out clever ways to do this at room temperature and atmospheric pressure. And so we've managed to distill down where some of this action is happening in this iron-sulfur complex. And we would like to model that to gain that understanding that I was talking about so we could hopefully build synthetic analogs at some point. But at the moment, an accurate description of the core of this has actually been beyond methods we know how to use on classical computers. And we're hopeful that we're able to attack this in the future with quantum computers. So classically, while there's not a clear path to an accurate solution, that's not to say there won't ever be one. We're hopeful that quantum mechanically, with 150 to 200 logical qubits, and logical is an important qualifier there, we're hopeful we can make good progress in understanding how these systems work. And so how do we actually start to make progress on these problems? And so, like I said, we're in the era before this vast quantum error correction technology is available. So we have qubits, which are not exactly perfect. They're a little bit error prone. And so we have a chip called bristlecone that we've talked about some amount of times, which has 72 qubits lined up in this kind of array here. And just to give you a barometer for what 72 qubits means, the projections for quantum supremacy experiments is that if you make an interesting enough state on 50 qubits or so, then that is larger than the largest memory capacity of a supercomputer on Earth today. So this slightly exceeds that, but like I said, they're imperfect qubits. So if the goal is the interesting simulation of some physical phenomenon, what the goal is not is to just run it on the largest system possible and kind of squint at the results. Say you see like a line going through there and that, yes, you've done it, mission accomplished. But that is not the goal. And actually on a real device, my prediction is doing an interesting simulation beyond 20 qubits will be very difficult without at least some form of error reduction techniques. And so if you do a quick sketch on the back of the envelope calculation, I'm not going to walk through all the details of what this is, but if you assume some very generous operation fidelity, meaning how good are my operations, and run it through a very short circuit, you find that your errors are much too large to be predictive on even small molecules. And so I'm going to talk a little bit about how quantum error correction theory can help us on near-term devices. And this is kind of a thought that's a little bit different than what people have done in the past, which is assume that quantum error correction starts at a very daunting number of qubits. And so what I want to say is there's some very basic concepts there that are transferable more broadly, and they actually have nice links to eventually what people will be linking quantum computers with HPC devices to do quantum error correction, but we can start a little bit before that. So to kind of go into which algorithms are most promising for NISQ today, and I have some amount of flexibility, I will say, in the amount of content I can cover since we started early, but I also don't want to run over if people are not interested. So, just flag when you need me to stop, and I'll. Otherwise, I'll go up until the time that I was originally allotted, which could be quite longer than what you might desire. So, so the quantum classical variational algorithms, in a nutshell, are this concept that we can take a lot of the problems that I've written down so far and at least recast their lowest solution as some form of minimization. And this is the trick that's going to let me make quantum circuits look like quantum neural networks to some extent and borrow a lot of the technology that comes from neural networks and use it in the classical case. And so this paradigm is that if I have some wave function, so this is just this state that I'm going to represent on my quantum computer, controlled by some set of parameters, and that might be something as basic as, say, kicking the device repeatedly in the same way, or turning the knob in the right way, or a more digital framework of it. I'm going to evaluate some objective and feed that into a classical optimizer that's going to update those objective parameters. And we've actually managed to turn a lot of problems into this framework, so chemistry, nuclear physics, discrete optimization, machine learning, algorithm learning. And it's a nice paradigm for a number of reasons. In particular, it's naturally noise resilient, and it allows you to say, take the quantum device that you have today and do as best you can with it. So rather than write down some huge algorithm and say, does it fit on my device? Maybe not. I'll say, take this device and give me the best answer that it can produce, which is a little bit a different way of asking the question. Of course, in the real system, we now have these different types of errors impacting it, which can make it very hard to use the system most effectively. And so a lot of the things that I've become interested in are how to learn from chemistry and physics and computing to bring in knowledge to reduce this amount of errors, to push out the boundaries of what we can do with these devices. And so one way of kind of exemplifying these quantum classical variational algorithms is with one particular experiment we did in superconducting qubits in 2016. And this, I think, is a very nice depiction because it lets you see the translation from the quantum software to the hardware and the link to the outer loop. So these are just two pictures of transmon superconducting qubits. And as you walk from left to right, you'll see in the software down here that we're enacting these gate operations. And these correspond to some pulse sequence or waiting time being applied to these qubits. And we stuck in here some kind of variational parameter down here that we then adjust and update with our classical algorithm. So this is what allows us to do this quick feedback and then get this kind of nice reduction in error. So I won't talk too much about this, but basically this problem is small enough that I'm able to exactly solve for the parameters on a perfect quantum computer that would be used, and I can compare them to what happens with this active feedback loop. And the active feedback loop is the errors in red, and green is what it would have been with a perfect device. So even though we tried our best to calibrate it, using this kind of paradigm, we're able to reduce the errors in a fairly significant way. And we have this interesting connection that I mentioned to quantum neural networks. And if you're familiar with classical neural networks and how deep networks developed, you might be familiar with the fact that there was this classical backpropagation technique, which for many years suffered from this vanishing gradient problem and to some extent still does. What we've been able to show recently is that there's actually a fairly interesting connection to this in the quantum case that also connects to the theory of information scrambling. So I don't want to talk too much about that other than to say that if you're someone that's into kind of the theory of applied math and Haar random unitaries, you might be interested in this kind of information theoretic scrambling phenomenon that can suck out and make it very hard to train these types of networks. So we were super interested in this result. And it, I think, guides actually how you would help to train these particular systems. And so the thing that I want to talk about next is something we actually managed to do while I was lucky enough to be at LBNL, collaborating with the people there and also Irfan Siddiqui's group, which was we wanted to go beyond the ground state simply by doing some extra measurements. And so we again wanted to hook up to this quantum classical interconnect where we do some measurements on a quantum device, offload it to a classical eigenvalue problem that I'm going to solve on, say, my HPC machine, and use that to improve my results. And actually, something that we found that was fairly surprising was that when we did this, so I talked about before this feedback loop that could have corrected coherent errors or like parameterization errors, this one actually impacted incoherent or random errors on my system. It was not very obvious why that happened, and it actually took some number of years for us to figure it out. And we actually did it by connecting it back to the theory of quantum error correction. So just to give you error correction at a glance, how does it work? It works based on redundancy and some assumption of likely errors to happen. So for example, basic classical codes, if you redundantly encode 1 0 as 3 and 1 1 as 3 1s, then if you have an error, you can figure out what your original state was supposed to be. And so for a while, people thought quantum error correction was impossible due to some basic physics, which is that it's impossible to clone an unknown quantum state because of the way quantum computers work. And measurement, as you know from Schrodinger's cat experiments, tends to destroy information or destroy states. So how do you use these two facts and at the same time manage to do some kind of quantum error correction? It turns out you have to change your conception of what it means to be redundant. So we hide redundancy in symmetries. And I won't get too much into the technical parts of this, but you can build codes that are very much analogous to classical codes, and you can build them as products of many of these. And so basically how quantum error correction works is you divide space up into allowed states and disallowed states, and you try to do information-preserving measurements to find out when you have an error and push yourself back. So we do this through kind of group theoretic means, which you may or may not be interested in, by specifying some symmetries and engineering them to be close to our error models. But essentially, one of the reasons that this was very hard to implement is kind of the actual mechanics of what you have to do. So what we did was come up with a slightly different way of doing it, which is to say, well, in the far term, if you want to do active error correction all the time, that's great. But in the near term, there's actually very cheap ways of doing a computation and simply throwing out the errored states. So we pay for a cost in sampling what we didn't have in operational fidelity. But this is a very nice mode of operation for near-term devices, which is that I can repeat many times quite cheaply, so I can get my rep rate up without having to have these extraordinarily long coherence times and still leverage the power and technology of these quantum codes. So moving through that, the kind of last thing that I wanted to talk about was not the details of this slide. In fact, you should just let yourself glaze over as you look at it, because the general message that I want to bring in here is that we've made a lot of progress, in particular in quantum chemistry, in the last couple of years. And the reason for that is that we've made essentially good collaboration between quantum algorithms experts and domain experts. And I think this is really crucial for the development, as it is in HPC, for success in quantum computing, is to not have some genius algorithm developer over here and some domain expert over here not talking to each other. It really depended on both bringing in knowledge from chemistry and from quantum algorithms. And this has been something that's especially hard to do, because if I just line up, say, the chemistry problem workflow, there's some sets of these, if you're familiar, that quantum chemists know extremely well, and the bottom that say quantum algorithms people know quite well. But bringing the two together makes it feel daunting to make any contribution, meaning how do you just enter and make the contribution at a point where you're an expert? And so to do that, we felt that it was kind of interesting to just build out an open source workflow that anyone could kind of come in, and I've just replaced each of those complicated steps with a few lines of Python that call an open source workflow. So if you feel like you can replace any particular part of this, you can swoop in and do so for a fairly low overhead. And we think these kind of domain-specific open source libraries are going to be crucial towards helping enable development in quantum computing, bringing experts in different fields together. So we're happy to have this Open Fermion framework that we now host on GitHub. You can go to openfermion.org if you'd like to learn more. And really, we like to do it with this kind of nice development philosophy where we really enforce Google Code standards, which we have found to be a very helpful way to keep the project going, make it easy for new developers to come in, because they'll find an abundance of tests, good documentation, continuous integration. So if a young student commits new code and it doesn't work, they're just told automatically by the system. It's not some ego-bruising process where someone says, this is crap. So I think it's a very welcoming and interesting way to kind of get involved in these. And we have, say, a release paper where we add students to this anytime they make any kind of contribution to the package. And we're hopeful that this is a growing community and a good tool, and that these will be developed, and they are being developed, in more and more application areas, say, closer to HPC. So with that, I'd just kind of like to summarize some of the things that I've mentioned. So I gave a broad introduction to a little bit of quantum computing, and to say that progress has been pretty rapid recently in algorithms and hardware. I think you're going to see some very exciting announcements, say, in the next couple years, or perhaps even sooner than that. And you'll have to have a little bit of a measured eye when you read them, but I think it's still valid to be excited. We talked a little bit about the challenges of how noise makes it difficult to get real answers on these near-term devices, but we're making progress in that area as well as we target these particular systems we think are important and build out tools to do so. And so with that, I'd just like to, again, thank everyone that was involved in this research, and again, the CSGF program for getting me started on this road. As I mentioned, I don't think without the early support of this program, this would have been entirely my research direction. So I was very fortunate in that regard. And so I'd like to thank all of you again, and of course, everyone in this room for listening. Thanks a lot.